So we have discussed log decrement in our previous class. Today we will be discussing about relaxation time. Uh, these are the factors which needs to be considered when we are discussing damped vibration. So relaxation time, what does it mean in a damped vibrator? Okay. So basically, you may be asked to define relaxation time of damped oscillatory system. You would be asked to show that it varies inversely as damping constant. You may have to derive an expression for relaxation period of a mechanical oscillator, electrical oscillator, and then how is it correlated to the logarithmic decrement of a system. So that is it. Okay, so we know that in a damped oscillatory motion, if we just plot the displacement with time, okay, the amplitude of the displacement with time, if we plot it, then we see that due to damping, and as all of you know, damping, it depends upon the frictional force, the resistive force that comes from for various reasons, friction of air, viscosity. Okay, so the amplitude decreases. Okay, so when we define this decrease of amplitude by various method, in log decrement, what did we take? If you remember, in log decrement, we took the ratio of the subsequent amplitudes. Okay, and we showed that this is always equal to a constant, the ratio of the subsequent amplitudes, in this manner. Okay, now you see, when we talk of relaxation time, it tells you the time in which the amplitude of damped oscillation falls to 1 by E of its original value. So starting from here, what is the time within which the amplitude will fall to, say, 1 by E of its original value? Say if this is your time, TR. Okay, so TR is the relaxation time at which the amplitude falls to 1 by E of its original value. Okay, all right. So, well, therefore, if A0 is the original amplitude of a damped oscillator, suppose, say, I consider the original amplitude. Let us consider this is the original amplitude which gets damped to A1, A2, A3 and then A4. Okay, so in this diagram, if A0 is the original amplitude, if this is your original amplitude of damped oscillator, the original amplitude of damped oscillator, okay, then, well, at what time A0 the amplitude A becomes equal to A0 by E. Okay, time at which the amplitude is equal to A0 by E, that time is the relaxation time. Now, because what is 1 by E? 1 by E is equal to 0.368. That is 1 by E. 1 by E is equal to 0.368. Okay, so whenever the amplitude of the oscillator falls to 36.8% of its original amplitude, then we say that the corresponding time is the relaxation time. So what conclusion can we draw from here? From here, the conclusion that we draw is that higher is the relaxation time. What can we conclude? If TR is high, what can we conclude from here? Higher is the relaxation time. Well, slower is the rate of fall of amplitude, and hence slower is the rate of dissipation of energy. So if TR is high, it means rate of fall of amplitude is slow. So that means dissipation of energy is slow. So this is very important. Dissipation of energy is slow, isn't it? So slower is the rate of dissipation of energy. Rate of dissipation of energy is slow. So, well, the amplitude of the damped oscillator at any given time, we already know that the amplitude of a damped oscillator at any given time A is equal to A0 e to the power minus of kt. What is k? K is the damping constant. So if T is the relaxation time TR, then A will be equal to A0 e to the power minus k TR, okay, which is equal to A0 by E, isn't it? A0 e to the power minus 1. So what can you say about, if you compare, what can you say? You will say KTR is equal to 1. So from here we conclude that the relaxation time is the inverse of the damping constant. Okay. It varies inversely as the relaxation time varies inversely as the damping constant. All right. Now, how do we correlate this to a mechanical oscillator? Suppose we consider a mechanical oscillator. You take a mechanical oscillator. Okay. So, how do we correlate? For a mechanical oscillator, what have we taken in our differential equation? For a mechanical oscillator, 2k is equal to R by M. So k is equal to R by twice M. K is equal to R by twice M. Hence the relaxation time TR, which is equal to 1 by K, it will be equal to twice M by R. That is the relaxation time, twice M by R, inversely proportional to the damping constant. Alright, now suppose we take an electrical oscillator. If we take an electrical oscillator, suppose say, for an electrical oscillator, okay, what do we have for an electrical oscillator? See, for an electrical oscillator, therefore, what do we get? Q, if we take the same equation for charge, amplitude of charge, okay, for an electrical oscillator, for an electrical oscillator, what do we get? You see, for an electrical oscillator, Q is equal to Q0 e to the power minus kt, isn't it? So, well, for TR equal to 1 by K, okay, Q will be equal to what? Q0 e to the power minus 1, which is equal to Q0 by E. Okay, so for an electrical oscillator, 2K therefore will be equal to what? 2K will be equal to, if you remember the equation for an oscillator with an LCR circuit, it is equal to R by L, where what is R? R is the resistance, L is the inductance. All right, so K will be equal to R by twice L. Okay, so TR, which is equal to 1 by K, is equal to 2L by R. Okay, so now suppose if you try to find out the relationship between log decrement and relaxation time. Now relaxation time TR is equal to 1 by K. And what is log decrement lambda equal to? It is equal to KT, isn't it? So you see, therefore, if you take 1 by K from here, 1 by K is equal to T by lambda, isn't it? So what do you have over here? Lambda will be equal to T by TR. So this is the relationship between the relaxation time and the log decrement. Okay, so let's stop over here right now regarding relaxation time. If you have any query, please let me know.